Hey there guys, welcome back to a brand new math video. Today we are going to be taking a look at Laplace transforms and how they can be applied to solving some questions. So firstly, let's first define what a Laplace transform is. So a Laplace transform is just some improper integral. And that it's improper because one of the domains, the upper limit, sorry, is going to infinity. Simply, that's what makes it improper. We must also assume that we have finitely many discontinuities. So, for example, the tangent function, that has infinitely many discontinuities because it repeats over and over and over with infinitely many discontinuities. It's as basic as that. So we cannot actually find a Laplace transform as such for that function. And okay, one of the ways that you'll likely compute a Laplace transform from the definition is via integration by parts. You should know integration by parts if you are studying Laplace transforms. It was in Calculus 1 or Calculus 2 depending on where you are studying. Now Laplace transforms, they can come up in both ODE questions and PDE questions. The PDE ones are different to the ODE ones in the fact that the PDEs uses partial differential equations, such as the partial derivative of u in terms of t, and the partial derivative of u in terms of x. However, in ODEs, they really only take effect in the one domain. So here, our definition is in terms of t, so we would look at t. Okay? And we can define the Laplace transform as this big function of f of s. That means s is our dependent variable after the transformation. However, before the transformation, it is independent. So if we had a multiple of s here, we could just drag that outside of the integral. It's that simple. F of t also must be exponentially dominated by the e to the minus st term. If it is not, and f of t is some bigger exponential function, then we have a problem. That would allow for our integral to diverge, and therefore we can't get a finite solution to the Laplace transform. Okay, so let's get straight into it by computing the Laplace transform of the sine of t, and I've actually done the calculation here already, so let me take you through the steps. So firstly, as indicated, we will be using integration by parts. We choose to integrate our term e to the minus st, and we get minus 1 over s sine t e to the minus st evaluated at 0 to infinity. And then we subtract minus 1 over s, that is from the e to the minus st term because we have to take the integral of that, but we also have to differentiate our sine term to get cosine t. So that's our v prime, and this is our u essentially. And that evaluates to 1 over s cosine t e to the minus st. So just our integral term here. So that's how we get to there, because sine of 0 is of course 0, and as this exponential term goes to infinity, it converges to 0, and therefore we just are left with this term. We now compute this. So all we're saying here is we're saying basically this, so this is just by the definition of what we're finding, the Laplace transform of sine of t, is equal to this integral evaluated, so we've just done the same thing, we've integrated in terms of the exponential term, and we get minus 1 over s squared cosine t e to the minus st, again evaluated from 0 to infinity, minus 1 over s squared times the integral from 0 to infinity of sine t e to the minus st. Notice this time we have a minus in front of here. This is because we had three minuses. So for example, we had cosine t. We differentiate that, we get a minus. We integrate the minus here, and we get the minus 1 over s again, and we brought that out the front. Hence we get s squared compared to this s. And we also had a negative from the definition of integration by parts. So that was uv minus the integral of uv prime or something like that. So that's how we get three negatives and we end up with a negative in the end. Okay, and from that we evaluate the integral here. And again, the exponential term, it converges. It converges to 0, whereas at 0, cosine at this time is 1, but so is this term. So we are left with a positive 1 over s squared because we're subtracting the lower bound. And we also add our copy of 1 over s squared multiplied by the integral from 0 to infinity of sine t e to the minus st, and there should be a dt there as well because that is what we're integrating in terms of. And here you should realize that, well, this integral here is the same as this integral here. So all we have to do now is some algebraic manipulations. So we subtract, actually, I'm sure that should be a minus. Yeah, so that should be a minus. So we add 1 over s squared sine t e to the minus st dt on both sides, and we can combine the fractions as such like this. That should be a white pen, so like that. And therefore, if we multiply by s squared on both sides, we would get 1. And then we divide by s squared plus 1 on both sides. And that gives us 1 over 1 plus s squared. And that therefore gives us the form of the Laplace transform of sine of t. So, let me rebrief. We went through the integration by part steps, and then we went ahead and we manipulated it using some algebraic manipulations, and we got to 1 over 1 plus 1, 1 over 1 plus s squared. And of course, if we had a different constant in here, how would that change? We will look at this in another video proving this, but what it would give us is omega over omega squared plus s squared. Something in that form. Okay, so now let's go ahead and let's take a problem where we want to compute the Laplace transform of f prime of t. In this case, we take a similar approach, and it's actually not so hard to do so. So what we want to do is we want to use integration by parts, and we want to integrate our derivative part. So that gives us f of t multiplied by e to the minus st from infinity to 0. And of course, as t goes to infinity, we use the definition that f of t must be exponentially dominated by the e to the minus st term. So in sense, that would mean that this would go to 0 as t goes to infinity. And then we evaluate at 0. Of course, e to the minus 0 is just 1, so you just get f evaluated at 0. And this thing here, as we defined up here, is nothing but f to the s. And therefore, we get f of 0 plus s of f of s. As we just stated, f of s is the Laplace transform of f of t, some function in terms of t. Okay, so our next step is I want to show that the Laplace transform is linear, and this one I'm going to go through, so bear with me here. So, we are going to take the integral of 0 to infinity, it's not that hard to prove this, of f of t plus g of t multiplied by e to the minus st dt. And straight away you can see that we can expand this. So we get the integral from 0 to infinity of f of t e to the minus st plus g of t e to the minus st dt. And now we can apply the linearity of the integral, therefore giving the integral from 0 to infinity of f of t to the e minus st dt plus the integral from 0 to infinity of g of t e to the minus st dt. And that is equal to the Laplace transform of f of t plus the Laplace transform of g of t. So that is an introduction to Laplace transforms. So to recap, we have shown the linearity of the property here. So if we wanted to compute, say, cosine t plus cosine omega t, we could use this property just to compute the two separate Laplace transforms. And we have done a couple of examples involving the derivative, which we will look at the second derivative next time. And we learned that we need to know one key piece of information on the function itself, and that is f naught. If we don't have that information, we cannot use the Laplace transform. And we also computed the Laplace transform of sine t.